Okay, in this video I'm going to continue on with exercise 4b of the book Fundamental Applied Mathematics. We're on page 104 and the question is 15. Now there are two parts to this question. One deals with the relative velocity vector and the next one deals with the distance of closest approach. So I'm going to do the first part quickly and the second part in more detail. So it reads, two straight roads cross at right angles. M and N jog towards the origin at two different velocities. We're asked to calculate the velocity of M with respect to N, and we're given a diagram in the book whereby we have the x-axis and the y-axis making our xy our Cartesian plane. We'll say this is N and this is M. We're told that the velocity of N is equal to 0 I hat plus 5 over 3 j hat. Like so, and we're given that the velocity of M is equal to 4 I hat plus 0 j. Alright, so this guy is going this way, this guy is going this way, like so. So we need to get the vector Vmn, which mathematically is very straightforward because it's Vm minus Vn. But of course the crucial thing here is, and this is absolutely crucial for the rest of this question, that we know that n is in a frame of reference whereby it believes that it is stationary. That is absolutely crucial. Alright, so let's just plug in the values which we know, and if we do that you're going to get Vmn is equal to 4 I hat negative 5 over 3 j. And that's correct. The next thing we're going to do is just going to sketch this vector. So it's in the positive I but negative j direction. So it's going like this. And this is going to be the vector Vmn. Alright, so if we want to resolve this, we need to draw the two vectors which when added together create this vector. They must be parallel to the x and y axes. So this is Vmn sub y and this is j hat. And let's move this out of the way here. This is Vmn sub x I hat. This is equal to 4. This is equal to 5 over 3. And it's not negative 5 over 3 because the negative is taken into account with the direction. So I'm going to call this angle here theta. Now of course we could also get this angle here alpha, but I know that the answer in the book corresponds to the angle theta. It doesn't really matter, but that's what they're actually asking for. So in order to get the angle at which this is at, we go tan theta is equal to the opposite over the adjacent is equal to 5 over 3 over 4, and if you inverse tan that you will get the angle theta. So theta works out to be approximately 22.4 degrees. That's correct as well. Sorry about that, you couldn't see that there. Now the next thing we need to do is get the magnitude of this vector, and that is very straightforward. It makes a right triangle here, so the vector, the magnitude of the vector is just Pythagoras' theorem. So you just get the square root of 5 over 13 squared plus 4 squared, and you root that. And you're going to get an answer of 13 over 3, which is also correct. Alright, so that's the first part done, and I wanted to do that pretty quickly. So the next part is we're asked to find the distance of closest approach, and we're given the following. We're given that when m, the vector or the position of m is at the origin, so when m is here, then n is at 0, 50. So they're 2 points. Now I suggest going on to page 93 and looking at exercise 4 or worked example 4.3, because it does this very concisely, very clearly, and it does it in two different ways. And all I'm doing is just following what the book essentially does, because it's a very good example. So how we do this is we need to get an equation of the line, a line first. So if I just get rid of lots of these things here, right? Just bear with me one moment now. So we still have the positions m and n. But we said we got the vector Vmn. And in that we knew that n was stationary. N was in the frame of reference whereby it was stationary. So let's just draw what Vmn looks like from n. It looks something like this. We're say this is m here. That's Vmn. And the distance of closest approach is when there is a 90-degree angle between these two vectors here like that. Alright? So we're trying to find out this distance I have in dotted. So the first thing I'm going to do is get the equation of the line of Vmn. So the equation of the line, in order to get the equation of any line, you need two things. You need its slope and you need 1 point. Slope and 1 point. Alright, so let's go get this. So we know of course that the vector Vmn was equal to 4I hat negative 5 over 3j. So the slope of this is just tan theta. Alright, so the slope of this was tan theta. So we're going to get Vmn is equal to the opposite over the adjacent, so it's 5 over 3 over 4, which is equal to 5 over 3 multiplied by a quarter, which is equal to 5 over 12, like so. And that is equal to m. Alright? Now, we also know another way of getting the slope. And that is by using the following formula. We know that m is equal to y2 minus y1 over x2 minus x1. So if we just rearrange that formula here, we're going to get y2 minus y1 is equal to m times x2 minus x1. And these are just points. Like, you know, you get 2 points. You're going to get the first point x1 y1, and another point x2 y2. And the thing is, you in your equation, in the general equation, you always leave this exactly as it is, but you actually plug in an actual point into x1, y1. So the question is this: have we any point on this line? And have we a slope? Well, we do have the slope. We just worked it out there at 5 over 12. And have we a point? So do we know any place where the vector Vmn, or the line Vmn, goes through? And the answer is we do, because we're told at some stage m is at the origin. Alright? And we know the vector Vmn corresponds to m, because n is stationary and m is moving. So if we know a position of m at any stage, we can plug it into this formula here and get the equation. So we know that m is at the origin, or 0, 0, like so. So let's just plug it in. The y and the x go away, and you're just going to get 12y minus 5x is equal to 0. And that's the equation of the line Vmn. Alright, that's pretty straightforward. Now the next thing we need to do is to work out the distance, the minimum distance from the position n here and that line. And the way we do this is by doing the following. You put in the position of n into the equation of the line, and you divide by the magnitude of the vector Vmn. So we knew, of course, that the vector Vmn was, or the slope, excuse me, so you divide by the slope. So the slope was 5 over 12. Alright? So if we want to get the magnitude of this vector here, it's going to be like it was 5x plus 12y. Alright, so to get the magnitude of this vector, it's just going to be the square root of 25 plus 144, which is going to be equal to 13. Alright, so what we're going to do is we're going to plug in the point which we want to test its distance from Vmn into this equation, and we're going to divide all that by the magnitude of the slope. Alright, or not by the vector which gave us the slope. So it's going to be, this is going to be 0. No, it's not. I'll take that back. What is the point? Sorry, first of all, what is the point? What did I say? That was 5 squared plus 12 squared, because the slope was equal to 5 over 12. Now, what point are we going to plug in? Where do we know n is? Well, we know that at some stage n is at the point 0, 50. That's the only thing we know. So if we plug this in here, we should get our answer. So x was equal to 0, and we know that y was equal to 12, or 50, excuse me. So what you're going to get is 600 over 13, and that's going to be equal to the minimum distance. Alright, so I'm not going to say that was straightforward, because that was reasonably difficult. I hope I explained some of it at least. Like I said, the example in the book is excellent. If there are any questions, please pass them on to me via a comment. So thanks for watching. Please pass it on to your friends and subscribe to my channel.